In section 6 of chapter 1, we're going to be graphing solutions to systems of equations. We just got done checking solutions. Now we're going to find them via graphing. This is not going to be the only way we find solutions to systems, but this is a nice little introduction because it starts with pictures. All right, so I want to do a quick little recap of what we just got done doing. We just technically started testing coordinates for solutions to systems. We had two equations, and we were testing to see if the coordinate provided was in fact a solution to both, which is my fancy math way of saying, is it where the two lines intersect each other? In this lesson, we're going to do the exact same thing. The only difference is, now, I'm not going to give you the coordinate. You're going to find it yourself, and then verify that you got the correct coordinate algebraically by plugging it into both equations.
Oh, that's not that bad.
So here's an example. I have two equations. I have y equals negative 4x minus 2. And if I graph that, then negative 2 represents the y-intercept. So it's where it hits on the y-axis. So it's going to hit at negative 2. So I go down 2, draw a dot. Then my slope is negative 4. It's the number in front of the x. Negative 4 over 1. So from my dot, I'm going to go down 4. 1, 2, 3, 4. Right 1. Down 1, 2, 3, 4. Right 1. I'm going to try and find where two lines hit. So I actually want a lot of dots. I could also go up 1, 2, 3, 4 and left 1. Up 1, 2, 3, 4 and left 1. Up 1, 2, 3, 4 and left 1. I want a lot of dots. I don't know where it's going to hit with the blue line, so I got to have a lot of dots just to cover my bases. There is the red line. Now I'm going to graph the blue line. Now I want to take a special note because there is something that I showed you earlier this year that I want to kind of put an asterisk next to. That blue function kind of looks like point-slope form, at least the way that you're used to recognizing it. You are used to problems like this. And graphing by finding a point and the slope from an equation written in this format. That was point-slope form. If I wanted to graph it, the coordinate would be the opposite of this, so negative 1, comma, the opposite of this, positive 2. And the slope would have been 3 over 2. This is considered an older, more archaic way of showcasing point-slope form. It is very common on things like the SAT, ACT, old-style assessments.
You don't have to take those anymore.
I know. I wanted you to be familiar with them, but we are going to slowly transition away from that formatting of point-slope into the new formatting of point-slope, which looks exactly the same, except we like the y value isolated. So all we do is move the number that is next to the y, we move it to the other side, and we write it at the end. The reason that we do that is because most technologies, most graphing utilities, if you want to graph something, they usually default to y equals, and then you plug in the equation. They usually default to having the y value by itself. So the newer formatting, which is already up there in blue, is we try and make the y by itself. That way, if we ever decide to use technology to graph, it's already set up for us. Now, the main difference between these two formats is the older methodology. You have to flip this 1 to make it negative. You have to flip this negative 2 to make it positive. If it's written in this newer format, in fact, let me get rid of the older format just so we don't get confused by it. If we are writing or utilizing this newer format, you still have to flip the 1. So the coordinate is going to start with a negative 1. But you do not need to flip this number anymore. It is going to be a positive 2. So that's my coordinate. Left 1, up 2. Left 1, up 2. That's my starting dot. The slope is still that 3 over 2 value. So from my blue dot, I'm going to go up 1, 2, 3, right 2. Up 1, 2, 3, right 2. You could also go down 1, 2, 3, left 2. Down 1, 2, 3, left 2. And you would create your blue line. me erase that coordinate. Now the answer to this problem, the solution to the system, is where the two lines overlap, where they intersect. That's going to be right here. That is going to be at this location, which is the coordinate -1, 2. This is the answer. I don't want you to be confused by that. That is the answer. That is the solution to the system. That's where the two lines overlap. However, I'm going to be asking more of you. Because who knows, maybe I screwed up when I graphed the blue line. Maybe I counted wrong. I need a process to verify that I got the right answer. And this is what we just got done working on. If I want to verify that that's a solution, I'm going to take that coordinate and plug it into both equations. If it is the solution, then when I plug it into both equations, I'll be left with true mathematical statements. So let's go through this. I'm going to substitute -1, 2 into my red equation. So it'll be 2 is equal to -4 times my x value, which is -1, minus 2. All I need to do is prove that that's going to produce a mathematically true statement. So that's going to be 2 is equal to -4 times -1 is +4. 4 minus 2 is 2. That is true. So far, so good. Next, I need to plug that coordinate into my blue equation. That's going to give me 2 is equal to 3 over 2 times the quantity of the quantity -1, quantity plus 1, quantity plus 2. -1 plus 1 inside the parentheses, that turns into 0. So I get 2 is equal to 3 over 2 times 0 plus 2. 3 over 2 times 0 is 0. 0 plus 2 is 2. It checks out for the second equation. Therefore, I know I got the right answer. I know that I didn't graph them wrong. I know I didn't count wrong. The answer I got by looking at my graph, that -1, 2, that is the correct answer.